Hello everyone, we're going to go through chapter 3b today. The first topic in chapter 3b is using a chemical equation to find the moles of product from moles of a reactant. This little meme here is very true, so we always want to convert into moles first. So most likely, with most stoichiometry kinds of problems you'll come across, convert to moles first. Then, if needed, you can convert into grams. And remember that conversion is using the molar or molecular mass, so in grams per mole. So in this first practice problem, wine goes bad soon after opening because the ethanol, we have the chemical formula there. The ethanol dissolves, reacts with oxygen, O2 gas to form water and aqueous acetic acid, and here's the formula for that. Acetic acid is the main ingredient in vinegar. So if your wine starts to smell a little vinegary after you've had the bottle open for some time, this is why. And ethanol is the alcohol ingredient in wine. So calculate the moles of ethanol needed to produce 0.070 moles of water. When I read a problem like this, I like to start thinking about what's being produced. So what are the products and what are the reactants? So here ethanol reacts with oxygen gas. The ethanol is likely in an aqueous solution, but we would not know that just right away from reading this problem. For a solution of alcohol in water, though, we would consider this ethanol an aqueous solution in water. So that's why we have this AQ here. So this should sound familiar from one of your post-lab questions. Then we're told aqueous acetic acid. This acid forms in the presence of water. So aqueous acetic acid means that water is also present. You would not be expected to write out a chemical equation from this sort of information. You should know oxygen gas is O2. You should know hydrogen is H2. So be sure you're keeping all the Brinkelhoffs in mind. So these are all the elements that form diatomic molecules. So CH3, COOH in the presence of water. This is also aqueous. It's submerged in water. It's dissolved in water. Water is a liquid here. Again, this is a more complex reaction that you would not be expected to write out at this point. What you should feel comfortable doing is taking this reaction and asking if it's balanced. If it's not balanced, then you should also be able to balance this equation. Let's find out if it's balanced. So we have oxygen, we have 2 here, 1 here. On this side, we have 1, 2, 3 as well. Carbon, we have 1, 2. So carbon, we have 2. Carbon on the product side, we have 1, 2. So carbon on the product side, we have 2 as well. Hydrogen, we have 1, 2, 3, 4, 5, 6. So hydrogen, we have 6. Then over here, we have 3, 4, 5, 6. So hydrogen, we also have 6 at this point. So this is a balanced chemical equation. Coming back here, we're going to convert into moles. And another super important detail here is we have to be working with a balanced equation. So balanced equation or balanced reaction, we have to have a reaction be balanced first before we do these stoichiometry problems. So again, at the center of these stoichiometry problems, we have to have a balanced chemical reaction. So be sure you're very comfortable with balancing chemical reactions, especially for these stoichiometry style problems. What's super helpful about these balanced chemical equations is these tell us the mole-to-mole ratios between the substances that are in the reaction. So this was introduced previously in chapter 3. So here, let's cover this again. So we have these mole ratios out front. What we can do from these mole ratios is say that for every 1 mole consumed of ethanol here, we have 1 mole of H2O that's produced. How do we know this? This is from our balanced chemical equation. So because this is balanced, there's this implied 1 right here for water. There's implied 1 right here for ethanol. That means that for every 1 mole of ethanol, we produce 1 mole of water. So the ability to write out this mole ratio is the huge benefit we get from this balanced reaction. So now we can actually technically connect 1 mole of O2 for every 1 moles of ethanol, 1 mole of O2 for every 1 moles of water. So for every 1 mole of O2 that reacts, 1 mole of water is produced. So really importantly, these molar coefficients from this balanced reaction helps us connect the moles of different substances, be it reactants to products. It helps us connect the moles of reactants as well, and the moles of the products as well. So balanced reaction is vital to writing out these mole ratios. So again, for every 1 mole of ethanol that reacts, we produce 1 mole of water. Now going back to our question, we're asked to calculate the moles of ethanol needed to produce 0.070 moles of water. So to solve this part, we have 0.070 moles of water. That's what we want at the end. And we want to calculate the number of moles of ethanol needed to produce this. Well, here is our conversion factor. So some other conversion factors we've seen, 1,000 milligrams in a gram, the grams per mole, or the molar mass of different compounds or molecules, or atoms as well. This is another conversion factor technically, right? So it converts 1 mole of ethanol to 1 mole of water and vice versa. So we can use this conversion factor to connect moles of water to moles of ethanol. Ultimately, we want to report the moles of ethanol needed here. So how do we orient this conversion factor to cancel out moles of water and just leave moles of ethanol? Well, we can use this conversion factor written out as is. We can say 1 mole of CH3CH2OH or ethanol for every 1 mole of water. Then we can cancel out moles of water, then we're left with just moles of ethanol. 0.070 times 1, so that's 0.070, so times itself, moles of ethanol. Okay, so we need to balance the reaction first, then use those molar coefficients to determine these different molar ratios. Here the mole ratio of ethanol is 1 mole of ethanol for every 1 mole of water. So here's our 1-to-1 mole ratio. We needed to produce 0.070 moles of water. So in order to do that, we are going to need 0.070 moles of ethanol. So that is our final answer. Should only have 2 sig figs here. So 1, 2 sig figs. Right, so these leading zeros are not sig figs. This 0 past this non-zero value, this is a sig fig because this value is less than 1. Okay, so just a little refresher on sig figs. Be sure you're keeping up with that material as well. And so again, here's our final answer. We needed to balance that reaction, then write out these mole ratios to get this as our final answer for moles of ethanol. So far we've written out a reaction and we figured out the mole coefficients. And we figured out how many moles of one product or reactant are needed to produce moles again of that product or reactant. What we're going to do next is start to venture into the use of grams. Still, though, we need to balance the reaction. We have to convert into moles first. We're going to use the coefficients from that balanced equation. Then, if needed in the problem, we'll then take moles into grams. But always, always moles first. For example, if you were given a mass of a compound A, you could use the molar mass to get moles of compound A. Using the mole ratio of A and B from, again, a balanced equation, then you can connect the moles of A to the moles of B. So really importantly, to go between mass of A and mass of B, we have to go into moles first. Then from moles of B, you can go into the mass amount or gram amount of B, again using the molar mass. So really importantly, again, one does not simply do stoichiometry without converting to moles. Okay, so we're going to convert to moles along the way here. Because it's so important, I put this additional reminder. We're going to convert to moles first. So now for this topic is solving for a reactant using a chemical equation. So now for this practice problem, we have some plants and they're undergoing photosynthesis. It's a reaction in which water and carbon dioxide chemically react to form glucose and oxygen gas. Now with this sort of description, you should feel comfortable writing out a balanced reaction. So we'd write out the reaction first and then see if it needs to be further balanced by adding any different molar coefficients. So we're told water and carbon dioxide react to form glucose and oxygen gas. That means water and CO2 are our reactants, right? So we write out reactants to products. So we have H2O plus CO2. These react to form C6H12O6 plus O2. So just by looking at this, we can tell that carbon is not balanced. So let's balance this equation first, and then we'll come back to solving the problem. So remember, we need to balance that equation first, then go into moles, then we can solve for grams. So to solve this, we can pick carbon or hydrogen, one that shows up in only one product and one reactant. Let's try carbon. So what do we need to put right here to make this have an equal number of carbon atoms? So there's 6 carbon atoms here, there's 1 here, let's add in a 6. So now we have 6 carbon and 6 carbon. What about hydrogen then? We have 12 here and only 2 here. So what do we need to add right here, or what coefficient should we put in to make this have 12 and this also have 12? So now we need a 6 right here. So now carbon on both sides, we have 6, hydrogen, we have 12 and 12. So oxygen remains. Again, oxygen can be trickier to work with in balancing these equations. There are 2 here and 6 here, so 8. Over here though, we have 6 times 2, so that's 12, and then 6. So here we have 18. So with 18 oxygens here and 8 in total here, what coefficient do we need to put right here to make both sides have an equal number of oxygen atoms? Well, this is a trickier one, so I'm glad I can show you this one. So we have 6 oxygens here and 2 here. And we have 18 over here. We need to take 18 and subtract 6, since we're not going to adjust this coefficient, just this one. So 18 minus 6 is 12. We need this set of oxygen, we need this coefficient to then have this be 12 oxygens, right? We're not adjusting this one, only this one with O2. We already have 6 here, we had 18 here, so there's 12 left to account for. We're going to account for those 12 oxygen atoms by adjusting the coefficient right here. How do we make this have 12 oxygen atoms then? Well, we can put in a 6, right? So 6 times 2 is 12. So now 12, and we no longer have 8 total. We have 12 over here and 6 here. So now we do indeed have 18 oxygens here and 18 here. So 18 here. Okay, so again, balancing equations with oxygen gets tricky, so let me know if you have any questions about this. So to check our work here, we do have 6, 6, coefficient of 1 here, and then 6. With that balanced reaction now, and using this diagram here, we're starting out the mass of some compound, ending up at the mass of another, and these are connected through this balanced chemical equation, and the mole ratio we get from that balanced chemical equation. The 2 substances we want to connect is carbon dioxide and water. Here's carbon dioxide and here's water. That means we only need to focus on this coefficient here and this coefficient here. So the way we'd write this out is for every 6 moles of H2O equates to 6 moles of CO2. And these are interchangeable, right? So we could have written it as 6 moles of CO2 for every 6 moles of H2O. So we have our balanced chemical equation. We need to convert quantities into moles. We do have this coefficient for the amount of water and carbon dioxide. So we have these coefficients here from the balanced chemical equation. Now we can work in moles and then eventually get into grams. So we determined this as well. The moles of CO2 consumed, 6 for every 6 moles of H2O consumed. Now that we've established the balanced chemical equation and the mole ratios of CO2 and H2O, now we can convert grams into moles of water, then take moles of CO2 and connect that to moles of water using this conversion factor. Then, since we went into moles, then we can take moles of CO2 to get the mass of CO2. In this question, again, we're asked about the mass of CO2 from this specified mass of water. So for the molar mass of water, we can go to the periodic table, look up the atomic mass of hydrogen and oxygen. We know that the formula for water is H2O, so 2 hydrogens and 1 oxygen gives water a molar mass of about 18 grams per mole, or 18 AMU. Here we're starting with 5.2 grams of water. So we're going to write that value out first, then write in our conversion factor. So remember, write the single number first, then incorporate the fraction. The fraction we're going to incorporate is about 18 grams per mole. So how do we orient this conversion factor to leave us just moles of water? Well, we should say 18.01528 grams of H2O for every 1 mole of H2O. Grams of H2O cancels out with grams of H2O, leaving just moles of water. Doing this division, we get about 0.28864 moles of H2O. So now we've taken the mass of water, and now we have the moles of water. Now we're going to use the mole ratio of water and carbon dioxide from that balanced chemical equation to get the moles of carbon dioxide. So we have this many moles of H2O. Our conversion factor here, so that's why I wrote this one first. It's not the conversion factor. The conversion factor we have, for every 6 moles of CO2 that are consumed, 6 moles of water are consumed. Right, so here's 6 and here's 6 for those molar coefficients. So a ratio of 6 and 6 does simplify to 1 and 1, but I'm going to go ahead and write it out fully here. So to leave just moles of carbon dioxide in the numerator, we need to say 6 moles of H2O in the denominator, then 6 moles of CO2 in the numerator. Then moles of H2O cancels out, moles of H2O, just left with moles of CO2. So we're essentially taking this value and multiplying by 1. So again, that's 0.28864, but now moles of CO2. So we're getting closer. So coming back here now, we do have moles of CO2. Now we can go into grams of CO2 using the molar mass of carbon dioxide, or CO2. For the molecular mass of carbon dioxide, we have 1 carbon and 2 oxygens. So this turns out to about 44 grams per mole, or 44 AMU. So here's our conversion factor for carbon dioxide. Then from the last slide, we know we have 0.28864 moles of CO2. How do we orient this conversion factor to leave just grams of CO2? Well, we should say 44.0095 grams of CO2 per mole of CO2. With that, moles of CO2 cancels out, leaving just grams of CO2 for our unit. Doing this multiplication, we'll get 12.7. Then to round this to the correct number of sig figs, so about 12.7 rounds to 13 grams of CO2. To say this is 2 sig figs, we don't technically need that decimal point there, but if it was 10 with just 2 sig figs, we would need that decimal point there. Right, so 10 with that decimal point, that's 2 sig figs, but just 10 written without that decimal point, that's just 1 sig fig technically. So coming back here, we did end up with the mass amount of CO2 in the end. Really importantly, we had our balanced chemical equation. And we went into moles. So we had to connect moles of A to moles of B, again, through moles, then we can get into grams. So really importantly, we make this connection between substances using a balanced chemical equation and the mole ratios in that balanced chemical equation. This next topic now, we're getting into the limiting reactant. We're going to identify this from a drawing of a mixture. Before going into this, what is a limiting reactant, or sometimes called a limiting reagent? This is a reactant or reagent that gets used up first in the reaction. For example, we have carbon monoxide and hydrogen gas. This forms CH3OH or methanol. You are not expected to know that this is methanol, but you should recognize this is carbon monoxide and hydrogen gas. So carbon monoxide is depicted here in red and black. So there are 1, 2, 3, 4 CO molecules. Then hydrogen gas is a diatomic, so you recognize this being 2 atoms of the same. So here's H2, there's 1, 2, 3, 4, 5, 6. So we have 4 CO molecules and 6 H2. Eventually these come together to form CH3OH. When looking at this transition, which one of these is going to run out first? Do we first use up all 4 molecules of CO to produce this product? Or do we first use up all 6 molecules of H2 to produce this product? So one way to see this is that for the product, we need 1 C and 1 O for every product. So 4 CO on its own could technically produce 4 CH3OH, just looking at the carbon and oxygen alone. For the hydrogens here, we need 1, 2, 3, and 4. So we need 4 H's for this end product. So we need 4 H's for this end product. That's 2 H2s. In total, we have 6 H2s. So for every 1 molecule of the product, we need 4 H2s. That means that 6 H2s would only technically make 3 of this product. So what can we say from this? H2 runs out first. So H2 runs out first, and we have excess CO. So CO is an excess because we can take 4 of these and make 4 of the end product. But to take 6 H2, we can only make 3 of the end product. So we'll make 3 of the end product and be left over with 1 of these COs. So this is how we can visualize this idea of the limiting reactant or limiting reagent. Really importantly, the limiting reactant on the reactant side will dictate or determine the amount of products that can be formed on the product side. Okay, so we kind of just deduced our way through this one, but I will show you chemically and mathematically how to figure out which one of the reactants is indeed our limiting reactant. So again, the limiting reactant is defined in the chemical reaction as the reactant that gets used up first. So another example is with non-chemistry, we can have a steam fitter bolting together pipes, has 6 nuts and 8 bolts. So 6 will run out before 8. So technically the nuts versus the bolts, these are the limiting reactant. Another example here with non-chemistry, we have 4 bicycle frames and 7 bicycle wheels. So now this one gets a little trickier to think about. So we have 4 bike frames and only 7 wheels. So 1, 2, 3, 4, 5, 6, 7. So we have this extra frame here with only 1 wheel. So the wheels ran out first. So the wheels here in this example are our quote, limiting reactant. Excuse my beautiful drawings here of these bikes. So now with chemistry, we have to have a balanced equation. This is a balanced equation. These coefficients are balanced. From a balanced equation, we can then know that for every 2 molecules of CH2 and 5 molecules of O2, when these react, we can form up to 4 CO2 or carbon dioxide molecules and 2 molecules of H2O. Right, so these molar coefficients also help us relate how many molecules of C2H2, how many molecules of O2 can produce how many molecules of CO2 and how many molecules of water. Then from a balanced reaction, we can draw out a visual like this. So C2H2, there are 2 of them. O2, diatomic, there are 5 of them. Carbon dioxide, there are 4 of them. So carbon in the middle with these 2 oxygens, then water, H2O, so there's 2 of them. Then based on what we're told about how much C2H2 or how much O2 is present, again, whichever one runs out first is our limiting reactant. The ratio here is that for every 2 molecules of C2H2 that react here, we need 5 molecules of O2. So this is how we connect how many moles or molecules are needed here to how many moles or molecules are needed here in order to produce, again, 4 carbon dioxide and 2 water molecules. If we only had 4 O2, then the oxygen would run out first. That would be the limiting reactant, right? Because we need 5 for this reaction to proceed for every 2 molecules of C2H2. And you would need a key like this to fully determine what is what. So here's red for oxygen, and here's the 2 whites for hydrogen. So from that balanced reaction, we again know that for every 2 molecules of C2H2, 5 molecules of O2 are needed. Here in this picture, we're given a collection of these molecules. So they haven't reacted yet, but this is what we have to work with. For oxygen then, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here we're just counting how much we're starting with. We'll come back to the balanced reaction as we're trying to figure out ultimately what is our limiting reactant. For C2H2, we have 1, 2, 3, 4, 5. So we're starting with 5 C2H2 and 10 O2. Then none of the products are formed yet, so these are still 0. So now in step 1, when we form 4 CO2 and 2 H2O, how much C2H2 and how much O2 was used up? Well, we needed 2 C2H2 and 5 O2 to form every 4 and 2 of carbon dioxide and water. So we had 5, but we need 2. So now we have 3 of these remaining. We had 10, we're going to use up 5. So now we have 5 of these remaining. So now we made 4 carbon dioxide and 2 water. And now we have 3 C2H2 remaining and 5 O2 remaining. So now to form 4 additional CO2 and 2 additional water. So it went from 4 and 2 now to 8 and 4. For the C2H2, we needed 2 more to make more of the product. So now we're using up 2. This leaves just 1 C2H2 remaining. For oxygen, however, we needed 5 here. So this minus 5. Then at this point, we have used up the oxygen. So here we have 1 remaining of C2H2, but we've used up all of our oxygen. So that means that oxygen is our limiting reactant or our limiting reagent. This is how we figured it out step by step. You could also possibly look at this final answer, this final step, and see, are there any O2 remaining? Are there any C2H2 remaining? There is one C2H2, but I don't see any oxygen here. So again, you could look at this visually or go through it step by step and really be sure in identifying which one is our limiting reactant. So something I want to clarify here is this distinction between the molar coefficients and the subscripts within the chemical formulas and within this reaction. So from this balanced reaction, what we can say is that the number of O2 diatomic molecules is 5. So 5 molecules of O2 are needed for this reaction to proceed. Similarly, the number of molecules of C2H2 is 2. So we need 2 molecules of C2H2 and 5 molecules of O2 for this reaction to proceed to produce 4 molecules of CO2 and 2 molecules of H2O. So that's what we can say from these coefficients. What we can also then connect is how many moles of a reactant are needed for how many moles of another reactant, or how many moles of a reactant are needed for this many moles of a product to be produced. We can also correlate this many moles of a product to this many moles of a product. So for example, for the products, for every 4 moles of CO2, there are 2 moles of H2O that are produced. So we can use these molar coefficients from this balanced equation to make all these mole-to-mole ratios. Then just looking at O2, for example, when we ignore this 5 because we're just focused on O2, we could say for every 1 mole of O2, there are 2 moles of oxygen needed for 1 molecule of O2. So now we're sort of ignoring these coefficients out here and just focusing on the subscripts when we're making connections about how many atoms are needed per molecule, or how many atoms make up each molecule. Then for instance, for every 1 mole of C2H2, there are 2 moles of H and 2 moles of C. We'd write this out as for every 1 mole of C2H2, there are 2 moles of carbon, 2 moles of hydrogen, so we could say 2 moles of C. Or this could be H as well, because these subscripts are 2 and 2. Now for this question, we're asked about the most initial moles and least initial moles. To make this connection and to figure out which has the most and which has the least, we can either work in molecules or we can convert molecules into moles. To convert molecules into moles, we're going to need to use Avogadro's number. So what does it mean if we can work in either molecules or moles to establish which has the least initial moles and the most initial moles? Well, looking at this picture, this tells us how many moles we start out with. Indirectly, though, it tells us how many molecules we start out with. So we counted up the C2H2s, there are 5 of them, right? And then the diatomic oxygen, there are 10 molecules to start with. Well, before we convert molecules into moles to confirm this, we can see that initially there are more oxygen molecules than there are C2H2 molecules. This is technically all we need to say that there are more moles of O2 initially compared to C2H2. Well, why can we say that if we have not yet converted molecules into moles? Well, let's do so and see what happens using Avogadro's number. So you start with 5 molecules of C2H2. We need to use this conversion factor with Avogadro's number. For every 6.022 times 10 to the 23rd molecules, this is 1 mole. When doing this in your calculator, be extremely careful to put this Avogadro's number in parentheses. So you want to take 5 divided by this whole number, but again, be really careful and put Avogadro's number in parentheses. So you can see that the substance, the identity, doesn't matter. It could be 5 molecules of anything. In converting molecules into moles, all we need is Avogadro's number. So 5 molecules divided by Avogadro's number. Again, we're really careful to put this in parentheses. So this whole value needs to be in parentheses. This gets us 8.30 times 10 to the negative 24th moles of C2H2. Now for oxygen, we start out with 10 molecules of O2. We still use this same conversion factor. So again, you can see the identity here is sort of arbitrary. We just want to convert molecules into moles. And again, we use Avogadro's number. This gets us 1.66 times 10 to the negative 23rd moles of O2. Comparing these exponents here, this is a smaller value with a negative exponent. So this is actually a larger number. How can we say that using scientific notation? Well, this would be moving the decimal point over 2 times, so 4 times 10 to the negative 2. Here we moved over 1 to 3 times, so 4 times 10 to the negative 3. This has a larger negative exponent. This is the smaller value. So this is a larger negative exponent. This is a smaller amount of moles. I know it's difficult to tell using these large exponents, so here's how we can think of that. The smaller negative exponent, that's the larger value. So again, this is the larger number of molecules of O2 to start with, and therefore also the larger number of moles to start with is for O2. Ultimately, what I wanted to show you is how we can also figure out the most initial moles and least initial moles. And also, again, be comfortable working with Avogadro's number here to go between molecules and moles. So as you see with this conversion factor, taking molecules into moles, we always divide by Avogadro's number. It doesn't matter what the species is, we would take 5 molecules divided by Avogadro's number. So there are initially more moles of oxygen gas compared to C2H2, and there are more molecules of O2 compared to molecules of C2H2. Okay, so most initial moles O2, most initial molecules also O2. Least initial moles C2H2, least initial molecules also of C2H2. And this is only looking at these reactants, by the way. So we're not looking at products here because we're focused on identifying the limiting reactant or limiting reagent. Now, combining these techniques, we're going to solve for the moles to moles in these limiting reactant style problems. In this practice problem, we have C2H2, again, so acetylene with oxygen gas, react to form carbon dioxide and water vapor. Now we have 3.0 moles of C2H2 and 2.0 moles of O2. Then we're asked to suppose as much as possible of the C2H2 reacts, how much C2H2 will be left? So C2H2 gas with oxygen gas reacts to form CO2 gas and water vapor, so also a gas. Let's balance this now. So we have 2 carbons over here. We can put a 2 right here. We have 2 hydrogens here and 2 hydrogens here. Oxygen then, it's trickier. So we have 2 here. So 2 and then 4 and then 1. So we have 5 on this side and 2 on this side. Oxygen does not also show up here, so we can just focus on this coefficient here for oxygen gas. How do we figure out what coefficient to put there? Well, now again, we don't need to worry about oxygen being present in both of these reactants. So we can take the larger number over the smaller number, and that becomes this molar coefficient. Now, this isn't our final answer because we don't want to leave a fraction as our coefficient, and we also need to check that we have the equal amounts of oxygen on both sides. Let's get rid of the fraction now. So what can we multiply 5/2 by to get this into a whole number or out of a fraction? We can multiply this by 2. So we want the smallest number that we can multiply this by. So 2 and 2, this would give 5. 5 is a whole number. That means we need to multiply this whole reaction times 2. That gives us then 2C2H2 gas plus 2 times 5 over 2. That's just 5O2 gas goes to 2 times 2, 4 CO2 gas plus 2 times 1, so 2 H2O gas. To check the oxygens now, we have 10, and then we have 4 times 2, that's 8. 2 here, that's 10. So 10 on this side and 10 on this side. No fractions, and these can't all be divisible by the same number other than 1. So we can't divide 5 by 2 or we'll reintroduce a fraction, and we don't want to do that. So now we have this balanced chemical equation, an extremely important step in determining the limiting reactant. We have to take this step in determining the limiting reactant. So based on what we know about limiting reactants, these stoichiometric coefficients tell us how much C2H2 and O2 are consumed in an exact 2 to 5 mole ratio. 2 to 5 mole ratio in our balanced chemical equation. So if 2 moles of C2H2 are consumed, then 5 moles of O2 must also be consumed. So 2 to 5 mole ratio, what about a 4 to 10 mole ratio? This also holds true. For every 4 moles of C2H2, so 4 moles, 10 moles of O2 are consumed. So you have that 2 to 5 ratio, that's equivalent to a 4 to 10 ratio, and so on and so forth. Now, a way to think about limiting reactants is what are the chances that a random mixture of C2H2 and O2 have exactly the correct mole ratios for all the reactants to be used up exactly at the same time? So here's our mole ratio, but what are the chances that we're given this certain amount of C2H2 that it reacts in a perfect ratio with the amount of O2 there is, that each of these is used up at the exact same time? Well, it's truly not likely. So that means that one of the reactants will normally be used up first, and this is our limiting reactant. When the one that's used up first, we can't produce any more product, the reaction can't go on any further. So how do we know if we're working with a limiting reactant style problem or an ordinary stoichiometric kind of problem? Well, if you're given just one reactant tells us we're likely dealing with an ordinary mole-to-mole or mass-to-mass stoichiometry problem. Alternatively, if you're given the amount of more than one reactant, you probably have a limiting reactant problem. For example, let's say we had 20 grams of this and then 100 grams of this. So here we're given a mass amount of both of these reactants. So if we're given the amount of more than one reactant, we again probably have this limiting reactant style problem. So let's continue this problem by finding the limiting reactant. There's a few ways to do this. I'll show you one alternative method called the Rice method in the next problem. One reliable approach here is to go through each reactant in turn, assuming it's the limiting reactant. Then calculate how much of the other reactants can be consumed when assuming this one is a limiting reactant. So only when you make the calculations for the actual limiting reactant will we get answers that make sense. We'll go through an example of this. Let's ask if C2H2 were the limiting reactant. So let's assume out of our two options, let's go ahead and assume first that C2H2 is the limiting reactant. If this is the limiting reactant, let's see how much O2 gas would be consumed. From the problem, we have 3.0 moles of C2H2 and 2.0 moles of O2. So let's start with the given amount of moles of C2H2, and let's go on assuming that's the limiting reactant. So 3.0 moles of C2H2. The really important conversion factor we need is to connect the moles of C2H2 to the moles of O2. For every 2 moles of C2H2 that are consumed, 5 moles of O2 are consumed. How do we orient this conversion factor now to leave just moles of O2? So here's this mole ratio here. For every 5 moles of O2 that are consumed, we have 2 moles of C2H2 that are consumed. This portion here is just from the balanced reaction. This portion here, this is our starting amount that's given in the problem. So again, we're told we start with this amount. This has no correlation to how many moles are in the molar coefficients. So we're given this amount and we're using this mole to mole ratio to figure out for 3.0 moles of C2H2, how many moles does that require for O2 given this mole to mole ratio? Moles of C2H2 cancels out, we're left with just moles of O2. That means for every 3 moles of C2H2, we need 7.50 moles of O2. So for this starting amount, assuming it's a limiting reactant, we actually need 7.50 moles to match this mole amount of C2H2. Do we have this many moles that were provided for us at the start of the problem? No, right? We only have 2.0 moles of O2. This means C2H2 is not the limiting reactant. So this is not the limiting reactant. It must mean that O2 is limiting. Let's go ahead and prove that as well. So we have 2.0 moles of O2. We're going to use this conversion factor again. We need to flip it so that 5 moles of O2 are in the denominator and 2 moles of C2H2 are in the numerator. Moles of O2 canceled with moles of O2. Then we get 0.80 moles of C2H2 are needed. So if oxygen runs out first, it's going to require 0.80 moles of C2H2. So we do have enough C2H2 to account for these 2.0 moles of O2. We would only need 0.8 moles of C2H2 for every 2.0 moles of O2 based on this mole to mole ratio here. Now we can say with certainty that O2 is indeed our limiting reactant. Let's go back to the question now. So suppose as much as possible C2H2 reacts, how much will be left? We only had 3.0 moles to begin with, and we only had 2.0 moles of oxygen to begin with. When we react all 2.0 moles of oxygen, we only use up 0.8 moles of C2H2. So we started with 3.0 moles. We subtract that 0.8 moles that was used up when we react all of the oxygen that we had. This leaves a final answer of 2.20 moles of C2H2 remain. So how much will be left? We just figured that out. So in rounding to the nearest 0.1 now, Then we report our final answer as 2.2 moles remaining of acetylene gas, or C2H2. There are some additional practice problems in the main slide deck related to limiting reactants, so be sure to check out example 3.15 and 3.16 in the main slide deck. For some additional practice as well, 3.13 and 3.14 are other examples from Chapter 3B that are in your main slide deck. And so those go back to solving for a reactant using a chemical equation as well.